and all the viewers who are watching this program live from Facebook page and YouTube channel. I would like to welcome you all to our International Physics webinar. Good evening to all. So hope you are well and safe from Corona pandemic. So today it's our 236 International Physics webinar, and today we'd like to welcome you all to a joint session between our Department of Physics, Pabna University of Science and Technology, Pabna, Bangladesh, and the School of Physics, Indian Institute of Science Education and Research, Thiruvananthapuram, India. And we have with us here today Dr. Bindusar Sahoo, sir, Associate Professor, School of Physics, Indian Institute of Science Education and Research, India, and he has already connected with us. So I'd like to welcome our speaker. Sir, good evening and thanks for joining with us. It's a great opportunity for our student to learn a lot of things about fundamental force. So before going to you, I'd like to introduce you with our student. So dear student and viewers, I think you have already come to know the title of the Students International Physics webinar. Title is the story of the fundamental force. I think you will enjoy this session because here you can learn about the four fundamental forces and about maybe some essence of fifth forces. And our speaker is Dr. Bindusar Sahoo, sir. I think you will enjoy it. So our speaker, Dr. Sahoo, has completed his master's degree from Indian Institute of Technology, Kharagpur, and his thesis supervisor was Professor Shankar, and he has completed his PhD degree from Harish Chandra Research Institute, Allahabad, and his thesis supervisor of PhD was Professor Ashok Sen, and then he went Italy for postdoctoral research at ICTP in 2009, and then he did another postdoctoral research uh, in 2011 from Institute of Theoretical Physics, Utrecht University, Netherlands, and he did another postdoctoral research from Amsterdam, National Institute of Subatomic Physics, and then he joined as the assistant professor in the School of Physics at IJR, Thiruvananthapuram, in 2013. So his research interest, currently he's interested in looking at the off-shelf formation of conformal supergravity with the force of supersymmetries, or in short N4 conformal supergravity, and they are trying to construct the action for N4 conformal supergravity with the knowledge of supersymmetry transformation of the well multiplate. And I think you will enjoy this session. So thanks for all of your patience. Sir, it's your time. You can start your session. And thanks again for joining with us.
Okay. Thank you, Dr. Pretam, for this nice introduction and for the invitation to speak at your International Physics webinar. I'm sure a lot of students would be watching it live, and I hope I can give them some nice story here. The title of my talk is the story of the fundamental force. Okay, so the force, F-O-U-R-S, it rhymes with force, and I am going to talk about four fundamental forces. And yeah, as you all know, there are these four fundamental forces: gravity, strong, weak, and electromagnetic. Out of which gravity is very familiar with all of you. Okay, it was originally formulated by Newton, and as the story goes, he saw an apple falling from a tree, and then he got this idea that there is a gravity force that pulls everything down, and and indeed this force is also responsible for binding our solar system, and all everything within our galaxy and universe is bound together by the gravitational force. Okay, so this is something very familiar. I mean, the most commonly observed force, however, very less understood also. We'll come to that later. The next most familiar force that with all of you is the electromagnetic force. Okay, it's basically the force that any charged particle observe. Yeah, so you have already all seen some magnet, how it pulls iron, iron, and you have also seen. You can also, do some small experiments with electromagnetic force. Charged particles have this force, and this is also a force that binds electrons and protons together inside the atom. So the electrons and protons are bound inside the atoms via this electromagnetic force. Okay, so these are the two most commonly observed forces. Gravity is rather the most commonly observed. Electromagnetic force is also very commonly observed. Maybe not as common as gravity, but yeah, at least at the high school level, you study about electromagnetic force and you do some small experiments with electromagnetic force. So this is also something very common. Then comes something which is not very common, but is there. The third force we all talk about is the strong force, and this is a force that is responsible for binding the nucleus together. So, as you all know, nucleus is made up of protons and neutrons. Neutrons are neutral particles. Protons are positively charged particles, and since the protons are light charges, therefore the electromagnetic force between them would make them repel each other, and the nucleus would fall apart. If there was only electromagnetic force, then the protons would repel each other, and the nucleus would fall apart. But that doesn't happen. So there is indeed some other force which is stronger than the electromagnetic force inside the nucleus, and this force is the strong force. Okay, and here we have a cartoon. Of how the electromagnetic force acts between nucleons. By nucleons, I mean protons and neutrons. Okay, so our current understanding of nucleons is that they are not fundamental, but rather they are made up of some quarks, and this U and D are the up quark and down quark that are there in protons and neutrons. Okay, so when it is a UDD, it is a neutron, and when it is a UUD, it is a proton, and they exchange some kind of particles. We'll come to that in a few moments. These are called gluons, and then these quarks are bound to each other inside the proton by exchange of these gluons. This gluons is responsible for the strong interaction, and then also finally, the protons and neutrons are tied to each other by exchange of some other heavy particle, which are called mesons, and I will come to that in a moment. Okay, so this is the strong interaction that is responsible for binding the nucleons together inside a nucleus. And then there is another interaction which is called the weak interactions. Okay, so far whatever interactions we have studied, electromagnetic force, gravity force, or strong force, these are basically responsible for keeping two things together. I mean, these are like responsible for forces between two particles. Weak interaction is a different kind of force. It is not force between two particles, but it is some different interactions that is responsible for some other phenomena that we observe in nature. So, for example, a nuclear decay. So we have if you have done some nuclear physics course, you must have come across this nuclear decay, and the most basic nuclear decay that we come across is called the beta decay. Beta decay is a decay where the neutron inside a nucleus basically converts into a proton via emission of a charged particle, which is an electron. It was called the beta particle to begin with, but it's actually the electron. There is some other particle that also comes out in this process, that is anti-neutrino. It's a neutral particle. Okay, so what happens is that okay, so this picture, if you see, so what is happening is that, as I told you earlier in the previous slide, a neutron is made up of U, D, and D quark, and the proton is made up of U, and D quark. So what happens is the D quark of the neutron becomes a U quark via emitting some charged particle, which is called the W minus boson. So it is a boson which is negatively charged particle. So the D quark emits a W minus boson and becomes an U quark, And that is how the neutron becomes a proton, and this W minus boson that has been emitted further decays into an electron and an antineutrino. Okay, that is the beta decay process, and this interaction via which this d quark becomes a u quark via emitting this W minus boson is a weak interaction process. Okay, so this is roughly the story of, a very short story of these four forces: gravity, electromagnetic, strong, and weak interactions. Okay. Now, so all those were like at a level of cartoons I explained, but in physics, when you look at the quantum theory, these interactions are mediated by some particles. Okay. In classical theory, for example, when you're looking at classical electromagnetic theory, you think of electromagnetic force as arising from some fields, from some electromagnetic field. So there is a charged particle which has an electromagnetic field. It creates an electromagnetic field, and when another charged particle comes in its electromagnetic field, it feels that electromagnetic field, and that is how they interact with each other. So that is in classical theory. In quantum theory, this force between these two particles is done by the mediation of some particles. So, for example, the electron interacts with another electron via exchange of a photon. Okay, so that is the electromagnetic force between two electrons via the exchange of a photon. Similarly, the strong interaction between quarks. So quarks comes in colors. Okay, so this is color doesn't mean that they're actually colored, but it is a term. Just like charge, just like electrons have charge, quarks have a different kind of charge. So it is a different kind of charge. It's not like the electric charge, but it is a different kind of charge, and that is called color. So that is why they are colored here, but actually they are not colored. So it is a different kind of charge, and that charge is responsible for strong interactions. So there is a green quark going to a blue quark via exchange of something called gluon, and that gluon carries a pair of color and anti-color. So it's a green anti-blue gluon, and that interacts with a blue gluon to give a blue quark to give you a green quark. Okay, so this is roughly the interaction between quarks via the exchange of gluons. This is a strong interaction. At a more fundamental level, this is a strong interaction between quarks via exchange of gluons. However, at a rather crude level, quarks are not fundamental. Quarks are fundamental particles, but they are not observed in nature. What are observed in nature is the protons, neutrons. Okay, these are the things that are observed in nature that are made out of quarks. Okay, so there is something called the confinement hypothesis, which states that quarks cannot be observed you cannot observe a free quark in nature. They will always come in some bound states. Okay, and these bound states are these protons, neutrons, and something called mesons, and there are particles similar to also protons and neutrons. Okay, so these are called hadrons. Okay, so the hadrons are more commonly observed in nature, not free quarks. So although the strong interaction between quarks is via the exchange of gluons, what happened because of this exchange of gluons, what happened that the neutron and proton interact with each other via exchange of another composite particle, which is a meson. Okay, so this is a diagram for that. Okay, so you can see that all these quarks that constitute the neutrons and the protons, they are all interacting with each other via the exchange of gluons. But at a more crude level, if you see, then these protons and neutrons are interacting with each other via exchange of this pi zero, which is a meson. Okay, and pi zero is a massive particle, and that is why the strong interaction between proton and neutron is short range. Okay, so whenever the force is mediated by some massive particle, the interaction becomes short range. That is, it is only felt at a very short distance scale. So that is why the strong interaction that binds the nucleons with each other is only inside the nucleus. Okay, if you break the nucleus, if you take them far apart, then the strong interaction will be negligible, and only the electromagnetic interaction will be dominant. But inside the nucleus, when the scale is shorter, then the strong interaction is more dominant than the electromagnetic interaction, and that is what binds the nucleus. Okay. So yeah, so this at a fundamental level, the strong interaction between quarks is via the exchange of gluons, whereas but the interaction between protons and neutrons is via the exchange of pi meson. Okay, and similarly here is a diagram for the weak interaction, where the neutron emits a W minus and becomes a proton. That is what we saw in the previous slide also, and that W minus further decays into an electron and an electron antineutrino, and this is the weak interaction. And these diagrams in quantum field theory are more commonly known as Feynman diagrams, because these were introduced by Richard Feynman to understand these interactions. Okay, so these are the three interactions: electromagnetic, weak, and strong. Okay, similarly, the gravitational interactions in the quantum theories should be mediated by gravitons, and that should be coming from some quantum theory of gravity. Okay, although gravity we understand very nicely at the classical level, but the quantum theory of gravity is very elusive, and that is what most people are after in the current century. Okay, electromagnetic weak and strong interactions are more or less very well understood, but quantum theory of gravity is something that we have not understood very well. Okay, so this gives so the electromagnetic strong and weak interaction of all the fundamental particles are nicely built into something called the standard model of particle physics. And this is rather an incomplete picture of the standard model of particle physics. I will come to the complete picture later and what is missing from here. Okay, so this picture tells you that what are the fundamental particles. So the fundamental particles are basically divided into three parts here. One is the quark sector, the other is the lepton sector, and the third one is the force carriers. So as we saw that the forces are mediated by some kind of exchange of particles. So those particles are here, and then there is a quark sector, and then there is a lepton sector. Okay, quark sector, we have seen up and down quark that makes up the proton. Okay, but there are other kind of quarks also that makes different kind of hadrons, which are not protons and neutrons. Okay, so there are charm and strange quark, there's a top and bottom quark. And similarly, the lepton sector is basically the electron and its neutrino. And similar to electron, there are other kind of leptons, which are muon and tau lepton, and corresponding neutrinos, muon neutrino and tau neutrino. Okay, so what we call lepton and what we call quarks is basically in what kind of interactions they can have. Okay, so for example, leptons cannot have strong interactions, so they are all put in leptons because they cannot have strong interaction. Quarks can have strong interaction, so they are all put in quarks. Okay, but quarks also have charge, so they also have electromagnetic interaction. Okay, and these are the force carriers. So the photon is the force carrier for electromagnetic interaction. Gluon is the force carrier for strong interaction, and the Z boson and the W boson are the force carrier for the weak interaction. W boson we have seen, but there is also a different boson that is also responsible for weak interaction, and that is a Z boson, and it's a neutral particle. Okay, so this is incomplete picture, and we will see why it is an incomplete picture. Okay. So the standard model of particle physics relies on a mathematical framework in quantum field theory, which is called non-abelian gauge theory. And this was originally expounded by these two people, Young and Mills, in 1954. And this is also known as Young-Mills theory because of that. Okay, it is something similar to your electromagnetic theory. So electromagnetic theory, those of you have done, is also a gauge theory. So electromagnetic theory also has a gauge transformation, and that is typically an abelian gauge transformation in the language of group theory. Okay. And this non-abelian gauge theory is a generalization of the electromagnetic theory, where the gauge transformation is not abelian but some non-abelian group. Okay, so I'm not going to discuss it in details, but it is some generalization. You can think of it as some generalization of electromagnetic theory. So these non-abelian gauge theory are used as a framework to understand the other interactions like strong interactions and weak interactions. And electromagnetic theory is understood by an abelian gauge theory. But all of them are gauge theory at the end of the day, and they have some gauge symmetries. Okay, it is either non-abelian gauge symmetry or an abelian gauge symmetry. Okay, And these gauge symmetries that are present in this theory, these prevent the elementary particles from having any masses. Okay, because mass for a particle means something from the point of view of the Lagrangian in the quantum field theory. So it's a very specific kind of term that you can put in the Lagrangian that will give you the mass for the particle. But this gauge symmetries actually prohibits those kind of term in the Lagrangian, and therefore within this framework of non-abelian gauge theory, you cannot put any mass for these particles. But experimentally, they are all observed to have have masses. At the same time, the framework of non-abelian gauge theory is very is able to explain a lot of other features of the interaction, but it is not able to give you the masses of the particle. So to overcome this shortfall, this technical shortfall, a possible solution is to spontaneously break these symmetries. Okay. So what do I mean by spontaneously breaking the symmetry? So spontaneous symmetry breaking basically means it's the realization of symmetry breaking in which the underlying physical laws are invariant under the symmetry, but the system breaks the symmetry. Okay. So what do I mean by this? So for example, if you take your Maxwell's equation, so this is the underlying physical law for the electromagnetic theory, and these Maxwell's equations are invariant under some symmetries. It is invariant under Lorentz transformation. It is invariant under translation. Okay, these are the symmetries of the Maxwell's equation. But if I give you a configuration in which I have a constant electric field along the z direction, okay, then this system breaks some symmetry. It breaks the rotational symmetry of around y-axis or along x-axis. Okay, so it breaks that symmetry. Although those rotational symmetries are part of the are symmetries of the original Maxwell's equation, but the system breaks that symmetry. So that is what is meant by a spontaneous symmetry breaking. Okay, so this one has to introduce a spontaneous breaking of these gauge symmetries so that the particles can acquire masses. And how is this spontaneous symmetry breaking introduced in standard model? Okay, this is an important question for the standard model. This was an important question for the standard model, and this question was answered by these three scientists, Brout, Englert, and Higgs, and it is known as the Brout-Englert-Higgs mechanism. And in this mechanism, one has to introduce a scalar field into the Lagrangian with some potential, and that potential is normally referred to as the Mexican hat potential, and looks like this. So this is the expression of the potential. So this phi is some complex scalar field, and so it has basically two components, two real components, the real part and the imaginary part. Okay, and if you take this potential and plot it versus its real and imaginary part, it looks something like a Mexican hat, and that is why it is called a Mexican hat potential. So if you see that the minima of the potential is not here, okay, is not here. So if somebody is sitting here, I mean, it's not the minimum energy configuration. So the vacuum cannot be here at phi is equal to 0. So this is the value of the potential at phi is equal to 0, which is not a maximum, it is a minimum. Okay, so the maximum, it's not a minimum, it's the maximum. Okay, so the minimum of the potential is over this green line, if you can see, okay, this green circle. So there is the minimum of the potential. So, but the minimum of the potential is not unique. It can be any point on this circle. Okay, so depending on where this field wants to sit over this green line, okay, you have to pick something, right? You have to pick up a point where you want to put your vacuum. Okay, once you pick up that point where you put your vacuum, your symmetry is broken. Your gauge symmetries are broken. Okay, okay. So this is the Higgs mechanism, Brout-Englert-Higgs mechanism in a nutshell. Okay, there is more to that, but I'm not going to get into that. But this is how you spontaneously break your symmetries, and this is how your particle will acquire masses. But in order to do that, you have to do something. You have to introduce a new field into your theory. And whenever you introduce a new field into your theory, the quanta corresponding to that field will become a particle. Okay, so there should be a particle corresponding to this field, and that particle is has to be observed. Then only one can accept this mechanism. Okay, so indeed that was a prediction of this Higgs mechanism, that there has to be a new particle that has to be in nature, but that particle is so heavy that you don't observe it immediately in any laboratory. For that, you have to build some sophisticated experiments to observe that particle. Okay, so that particle was initially called, people call it as a Higgs boson, but that particle was not observed until 2012, where it was observed at this place called the Large Hadron Collider. So this Higgs boson, the Higgs mechanism was formulated in the 70s probably, but the particle was finally observed by a very sophisticated experiment at this Large Hadron Collider in 2012, and that led to the Nobel Prize that was awarded to these two gentlemen, Englert and Higgs. Although Braut was also a part of that mechanism, but since Braut was not alive and the Nobel Committee do not award prize posthumously, so it was only awarded to Englert and Higgs. Yeah, so this is roughly the story of standard model of particle physics, and then that makes this picture complete. So what we had earlier was only this part, and now the missing part, the Higgs boson, is here. And now with this, the standard model of particle physics is complete, and it explains almost all experimental observations that we observed at the subatomic level. But standard model also has its drawbacks. Okay, and what are the drawbacks of standard model? So the first drawback of standard model is that it does not incorporate gravitational interaction. So the standard model relies on the framework of quantum field theory, and the framework of quantum field theory breaks down for general relativity at higher energy. So gravity is described by Einstein's general relativity. So the classical field theory that explains Einstein's general gravity is Einstein's general relativity. And if you want to understand gravity at the quantum level by applying the quantum field theory framework, that has its problem. Okay, and it breaks down at higher energy. Okay. So this is one of the shortcomings of the standard model, that you cannot incorporate gravity because standard model relies on the framework of quantum field theory. And there can be many solutions to that. One of the solutions I have written down here is string theory. Okay. There is another problem with standard model is called the hierarchy problem, and it's a more technical problem rather than an actual problem. Again, coming from the framework of quantum field theory, the hierarchy problem basically, at a very rough level, states that the weak scale is much smaller than the Planck scale. The weak scale is of the order of GeV, some 200 GeV, and the Planck scale is 10 to the power 19 GeV. And because of this hierarchy between weak scale and there is nothing between weak scale and Planck scale. And at a technical level, it requires severe fine-tuning of parameters. So if you do quantum field theory calculations, you will see that the parameters that has some specific value experimentally from the quantum field theory point of view, it has to be severely fine-tuned. Okay, so that is a very technical problem with the framework of perturbative quantum field theory. And the solution to that is, to go beyond standard model, where you introduce extra dimensions or something called the supersymmetry. The supersymmetry is a different kind of symmetry that relates bosons to fermions and vice versa. Okay. The third problem that I can list here is inconsistency with the standard model of cosmology. It cannot explain the observed amount of dark matter and dark energy. So cosmology tells us that there has to be some matter outside what is given in the standard model of particle physics. So standard model of particle physics has leptons and quarks and all these things, but which has electromagnetic and strong and weak interaction in a certain way. But standard model of cosmology, what we cosmologists observe, there are some other kind of matters that have interactions quite different from what standard model particles can have. These are called dark matter, and standard model doesn't explain how dark matters arise. And one solution is supersymmetry. So there is a supersymmetry extension of standard model which can have a candidate particle which has the properties of a dark matter. So that is also one solution. Then there is an aesthetic problem with standard model. I mean, this is not more of a problem, it's an aesthetic. I mean, it has 19 arbitrary parameters which has to be fixed from experiments. Okay, so it would be nice if you can explain everything from one single parameter or something like that. And then the solution to that is also string theory. And then there are other problems that I have not listed here: matter antimatter asymmetry, neutrino masses, and all these things that also requires going beyond standard model. Okay, so going beyond standard model is one of the focus of current generation particle physicists, and they're working on various models, how to go beyond standard model and how to explain much of the problems described here, except gravity. Gravity has to be discussed separately, and some quantum theory of gravity will be able to explain it. Okay, so yeah, so that brings me to my next uh, next part of the talk, which is on string theory, because that is one of the candidates that can explain gravitational interaction at the quantum level. So what is string theory? So string theory, roughly, what you do is you say that instead of point particles, we have one-dimensional string. Okay, and this string basically classically can oscillate in many different ways. And when you quantize it, each of these different modes of oscillation, this corresponds to different particles that we observe. Okay, and among all the different particles that you get from quantizing these modes of oscillation, one of the particle corresponds to the graviton, which I had earlier told you is something that should arise from the elusive quantum theory of gravity. So string theory is that elusive quantum theory of gravity, which gives you that particle, that graviton. Okay. So yeah, so your Feynman diagrams, which I had introduced earlier, was for point interaction of point-like particles. In string theory, it is replaced by some two-dimensional surface, which is the interaction of strings, and you can see that the interactions, instead of happening at a point, is smeared over a surface, and that is what is responsible for having a well-defined quantum theory of gravity. So the problem with general relativity breaking down at higher energy within the framework of quantum field theory, which was more of a framework, the quantum field theory framework was more of a framework for explaining interaction between point particles. So that if you replace it with strings, then the problem of gravity breaking down at higher energy does not arise. Okay, so at higher energy, one should be rather doing this kind of Feynman diagrams rather than this kind of Feynman diagrams, and one can show that if you go to lower energies, this kind of Feynman diagrams will reduce to this kind of Feynman diagrams, and you will get everything that you have already successfully verified at lower energies. So it's a kind of consistent way to do things. Okay, yeah. So some of the features of string theory is that you need extra dimensions. Okay, string theory is consistent in 10 space-time dimensions, so 9 space and 1 time. And whereas the original, I mean, our real universe that we are living in is 3 space and 1 time. So there are 6 additional space dimensions that are there, and so they have to be curled up into tiny, small, little compact manifolds. And yeah, so that is one feature of string theory. So you need to compactify your 10-dimensional theory in on some 6-dimensional compact manifolds, and these compact manifolds are called Calabi-Yau manifolds, named after two mathematicians, Calabi and Yau. And another feature of string theory that is you need supersymmetry. So if you don't have supersymmetry, you will not be able to explain fermions, and in our actual universe we have fermions, all the quarks and leptons that we had seen earlier. These are fermionic particles. So supersymmetry is essential for getting fermions in the spectrum. And as a result, the low energy feature of string theory is not just gravity; it is gravity combined with supersymmetry, and that is called supergravity. Okay, so you just don't get just gravity out of string theory. You get gravity combined with supersymmetry, which is a supergravity theory. So its supergravity is not the complete string theory, but it is the description of the low energy sector of string theory. Okay, so there are other highly massive particles in string theory that you have to sort of because they are very highly massive, they are only relevant at higher energy scale. So at lower energy scale, these highly massive particles don't play a role, and whatever particles at the low energy scale plays a role, that combines together with gravity because of the supersymmetry, it gives you a supergravity theory. Okay. And another feature of string theory are something called the D-branes. Okay, so these are some objects. So string theory, you have these open strings, closed strings, and so on. So when you are, when you want to solve equations of an open string, so these have endpoints, and you have to supply boundary conditions for the endpoint, just like any classical problem. And these boundary conditions of the open strings endpoints are the D-branes, basically. So these are essentially objects where the open strings can end. These are objects in your space-time where open strings can end. These are called D-branes. And also these D-branes arise as some sort of solitonic solutions in the supergravity theory. So these have description either in the open string formalism, where they as the endpoints of the open string, or as some kind of solitonic solutions for the supergravity theory. So these are some, there are many features of string theory. I'm just focusing on some of the relevant ones for my talk. Okay. And yeah, so these are some of the features in string theory. So now I will discuss something relevant for this talk about black holes in string theory, and it will be clear why I want to discuss that. So black holes, I think many of you are aware of. These are some classical solutions to theory of gravity, and these are These are such solutions that they have some kind of membrane, which is like a one-way membrane, but things can go in, but nothing can come out. So yeah, so that is the feature of black hole, that classically nothing can come out of it, not even light. But Stephen Hawking gave us a different answer. He said that if you include quantum effects, black holes radiate. And the rough way of seeing how this is known as Hawking radiation, and the rough way of seeing this Hawking radiation is via this picture. So when you have quantum effect, in our vacuum, this pair creation always keep on happening. Particle antiparticles pair are created. If they're far away from the black hole, these antiparticles that are created, after some point they get annihilated, and so this keeps on happening. But close to the horizon, if a particle and an antiparticle pair gets created, and the antiparticle falls into the black hole and the particle comes out, then they are not annihilating each other, because the antiparticle that has fallen into the black hole cannot come out of the black hole. So for an observer very, very far away, it will look like the antiparticle essentially goes into the black hole and annihilates some particle inside the black hole, and the black hole loses some mass. So for an observer very, very far away, it will look like the black hole is losing mass, and whatever mass it is losing is coming out as radiation. So this is basically your Hawking radiation. And so just like any object which radiates, a black hole also radiates in this way when you include quantum effects, and therefore it has some temperature as well as entropy. Okay, so just like any thermodynamic object, these black holes have temperature as well as entropy. Okay, and you have all studied in class in statistical mechanics that entropy is a measure of the number of quantum states accessible to the system, and it is given by the Maxwell-Boltzmann's formula. Okay, So if omega is the number of quantum states accessible by the system, then the entropy is given as kb log omega. Uh, yeah. So kb is the Boltzmann's constant. Okay. And so if something has entropy, so black holes has entropy, and we can compute this entropy of these black holes in a theory of gravity. Okay. And given by this Bekenstein-Hawking formula or Walsh formulation. These are various people who have told us how to compute the entropy of a black hole. Since we can calculate this entropy, it means that black holes have some microstates that are accessible to it. Then the question is, what are these microstates? Okay. So string theory gave us a way to construct the quantum microstates that are accessible to a particular kind of a black hole. So string theory doesn't give an answer to a very generic class of black hole, but to some specific class of black hole, string theory gives us an answer on this question: what are these microstates accessible to the black hole? Okay, and these black holes that string theory deals with have either zero temperature or very small temperature. Okay, so these are in a sense not real black holes that you observe in universe, but these are some kind of black holes that we are using to understand understand string theory better. Okay. So these microstates are constructed in string theory using all the objects that are there in string theory, as I had told you earlier. Like these d branes are there, and then the internal manifolds are there, and you can wrap these d branes on some cycles of the internal manifolds, and then there can be fluxes, etc., etc. So there are many things which I'm not going to go into details, but you can actually construct the microstates of these black holes, and there will be many such configurations that you can construct that will correspond to the same black hole with same mass, charge, and angular momentum. So these are basically the microstates that are accessible to the black hole. And counting such states and using the Maxwell-Boltzmann's formula gives us what is the microscopic or the statistical entropy of the black hole. So for that, one needs better understanding of string theory. Okay, so that is where a lot of people work on how to count these states, how to effectively compute the microscopic entropy of the black holes. And on the other side, you need to compute the gravitational entropy of the black hole from the theory of gravity. In this case, it's the theory of supergravity, because as I said, string theory not only gravity, it doesn't just give you gravity, it gives you supergravity because of supersymmetry. Okay, and there are these gravitational techniques to compute the entropy of these black holes, as I said, like the Walsh formula or the Bekenstein-Hawking formula. Okay, and you need to understand supergravity better in order to compute this side of the entropy. Okay, and then you have to check whether this side and that side match with each other, and if there is a matching, then you say that okay, the theory of quantum gravity, that is string theory that I started with, is at least mathematically self-consistent. So in this sense, the black holes that we are using to study string theory is a kind of a theoretical laboratory to test the ideas of string theory. So they may not be real black holes, but these are kind of theoretical laboratory to test string theory, whether it is mathematically self-consistent or not. Okay. So any theory of quantum gravity has to pass this test before even going for experimental verification or not. Any theory of quantum gravity has to pass this test. So for a very, very specific kind of black hole, string theory does pass this test. Okay, and therefore we think that we are on the right track. Okay, so that is one of the triumphs of string theory, if you may say. Okay, and so whether there are some, like, whether string theory is just an idea which is very, very far away from experimental verification, because if you want to experimentally verify any ideas of string theory, it may need very high energy scales, and currently we have not reached that scale. So it's very, very far away from any experimental verification. But then is it just a theoretical idea that we have to live with, or does it give us any application to the real world physics? And yes, something that has originated from string theory has actually given us tools to apply it to some real world phenomena. Okay, and that thing that has originated from string theory that gives us a tool or a framework to deal with real world physics is called ADS CFT correspondence, and it was originally formulated by physicist Joan Maldacena. And so what this ADS CFT correspondence tells you, so ADS stands for anti-de Sitter space-time. So it's a specific kind of space-time that has constant negative curvature. And CFT stands for conformal field theory. So it is a specific kind of quantum field theory with conformal symmetries. So there is some kind of symmetries called conformal symmetries, and it is a very specific kind of quantum field theory which has conformal symmetries. Okay, so what this ADS CFT correspondence tells you that if string theory on some ADS space times some compact manifold here. So since our string theory originally in 10 dimensions, so if you have some ADS n, then there is some compact manifold of 10 minus n dimension. That is the same as quantum field theory on Minkowski space of n minus 1 dimension. Okay, so this is the idea that originated from string theory. Okay, so this is it was originally for ADS 5 times S5. ADS 5 is a 5-dimensional ADS space-time, and S5 is a 5-dimensional sphere. So what Joan Maldacena showed is, that he didn't prove it, but he showed that string theory on ADS 5 cross S5 has something that you can calculate, and that sort of agrees with a specific kind of quantum field theory on Minkowski space of 4 dimensions that is called the n equal to 4 super Yang-Mills. So it's a supersymmetric theory, supersymmetric version of the Yang-Mills theory. And so this idea had originated from string theory, and this has been applications in many different areas. So one application is in this thing called quark-gluon plasma. So quark-gluon plasma is a phase of quantum chromodynamics. Quantum chromodynamics is the theory of strong interactions, and it consists of free quarks and gluons, and is hypothesized to exist at extremely high temperature, and is observed at some laboratory, for example, the relativistic heavy ion collider, RIC. Okay, so these are observed, and the physics of quark-gluon plasma is intractable using standard perturbative techniques of quantum field theory because of strong coupling. So the perturbative techniques of quantum field theory can apply when the coupling is weak, but because QGP has strong coupling, you cannot use the standard perturbative techniques of quantum field theory to study the physics of QGP. However, ADS-CFT correspondence allows you to map a theory that is almost similar to the theory of QGP. It is not exactly QGP, but it is almost similar to the theory of QGP. You can map it, and this ADS-CFT correspondence, I have not mentioned it, but it is a strong weak duality. So a strongly coupled field theory is related to a weakly coupled string theory, or a strong, and vice versa. So if you have a strongly coupled field theory, which is the QGP, you can map it using this ADS-CFT correspondence to some weakly coupled gravitational theory. It should be full string theory, but you can just focus on the gravity sector of the string theory, and you can forget about the other sector of the string theory, which are highly massive for the energy scale that you're looking at. So you can couple it to weakly coupled gravitational theory, which becomes a classical gravity theory, and you can do some classical gravity computation, and you can extract useful quantities out of that. So this is one advantage of ADS-CFT correspondence. It has also been successfully applied in many condensed matter systems, so to understand some critical points of condensed matter systems. And so these are some of the applications that has originated from string theory because of this ADS-CFT correspondence. So I think I have more or less finished my talk. I would like to end with these two quotes by two famous physicists, Brian Greene and David Ross. You can read it, and it is self-explanatory. Okay, thank you.
Thank you, sir, for your wonderful and exciting presentation, sir. I think you have explained this thing very clearly, and I think students and viewers have learned a lot of things about the string theory and particle physics and the four fundamental forces. So we have got few questions. So if you allow us, so we can start our discussion sessions.
Sure, sure.
So first question: what is the reason behind the extreme small mass and the magnetic moment of neutrino?
Okay. Yeah, so these are these are observed things. So the extreme small mass, these are observations, and yeah, one is trying to incorporate this into the standard model. That is what I said. Some of these standard model does not give you any mass of the neutrino or anything. So you have to formulate some theory by going beyond the standard model, which can explain this theoretically. That is what I said, that you have to go beyond the standard model. And there are theories that actually explain the small mass of the neutron. Yeah.
Okay, so thank you. We have another question from the same person. So can string theory explain and unify all the fundamental forces?
Yes, that is what string theory does. Yes, so it unifies all the fundamental forces. As I said, when you when you take this string and you quantize all the oscillation modes of string theory, you get different particles. So you get all the particles responsible for all the four fundamental forces, and that is a way to see that string theory unifies all the four fundamental forces. But yeah, so whether it gives you something like exactly same as we observed, like whether it can reproduce standard model, that is the main question that we all should ask, whether string theory can reproduce standard model. So that is something that people are looking at. Currently I don't think there is a concrete answer to that question, but this is something that we should be looking at. Yeah.
Okay, sir. Thank you, sir. We have another question. Sir, how do the four forces exert its force? Does it require any particle?
Yeah, that's if I understand the question correctly, the forces in, as I said, in quantum theory, the forces are due to the exchange of the particle. Like for example, if you want to understand the force between two electrons, classically, how you understand it? You say that there is one electron which creates an electromagnetic field, and the other electron feels that electromagnetic field, because of which there is a force between them. In quantum theory, you say that this electron is emitting a photon, and this other electron is absorbing that photon. And it is like, if you're taking a gun and shoots a particle, you feel the recoil force. And the other person who is absorbing that particle also feels that recoil force. That is how, it's in a cartoon way, but this is a way you can understand it, that these electrons are emitting photon. One electron is emitting photon, the other electron is absorbing photon, and that is how it is experiencing this electromagnetic force.
Yeah, thank you, sir. We have another question. So, can we experimentally verify string theory in near future?
Okay, that's a good question. Unfortunately, I don't have an answer to that. Yeah, so yeah, I don't know from where the experimental verification will come from. I mean, clearly, if you want to verify by constructing some kind of accelerators or something, you need to have sophisticated technology which can access that energy scale, or whether it can be some experiments coming from cosmology, some early universe. I mean, trying to observe something from early universe where the quantum gravity phenomena would be dominant. If you can make some experiments, cosmological experiments, and try to do that, that might be, but still you will need very sophisticated technology to do that. And so far, we do not have those sophisticated technologies. So I don't know in near future what does it mean. I mean, whether it is 500 years or 1,000 years. Yeah, so not at least, I mean, I don't see any experimental verification in our lifetime. Maybe it happens someday. Yeah.
Okay, so thank you. We have another question. So, do we need experiment to probe into the regions below the Planck scale to have useful data about how gravity works on a quantum mechanical level?
Regions below Planck scale. I mean, yeah, I mean, if you are asking that, if it is something very below Planck scale, like something comparable to weak scale or something, where we have access, then yeah, I don't know. Like if you can have some experiments at the weak scale, which can give you data on quantum gravity. I'm not sure about that. You need some Planck scale experiments, and currently that is out of reach. Yeah, with big scale experiments, I don't see how you can get data about how gravity works and quantum mechanical.
Okay, sir. Thank you. We have another question. This may be the last question. In the future, will we understand quantum gravity? What do we need to make it possible, and how can it be tested?
Okay. In the future, will we understand quantum gravity? Okay. Yeah. So basically, right now, people should work on various different ideas of quantum gravity. One should not be relying only on one or two ideas. Perhaps people should work on many ideas, and perhaps when we can actually access those energy scales or something where we can test ideas of quantum gravity, then experimental verification will either rule out or not rule out certain ideas. So, yeah, so that is how we should. I mean, until we can do the experimental verification, I think it is fair enough to say that we should be working on many different ideas. Yeah.
Okay, sir, thank you for your wonderful presentation and discussion session. It was a great webinar. I think students and the viewers have learned a lot of things about four fundamental forces and the string theory. So the main aim of our program is to motivate our students. I think by your lecture, some of our students and the viewers are already motivated, and hopefully they will join in this research field near future. So thanks for giving us this opportunity to arrange such an important webinar. So bye for today, and hopefully we can arrange another exciting webinar with you in near future.
Thank
Have
you.
a
Thank
nice
you.
night,
Thank
sir.
you. Thank you.
Bye.
Thank you.